Can anyone share the YouTube link on the WhatsApp group? I'm not logged in WhatsApp today. All right. So let us get started. And today, what I will discuss. Today, what I will discuss is a slightly slightly different phase fluctuation phenomena. So it is again a phenomena that is related to the phase in a superconductor. However, this is not really the long wavelength phase excitation. So this is topological defects. What are topological defects and how we deal with that? So let's go ahead and you will understand. Okay, so for this, what we will start with has actually not much to do with superconductivity. Okay, is my screen visible?
Yes, sir.
Okay, so what we will be studying in this last bit of the course is Berezinski Kosterlitz-Thouless transition. By the way, though the TIFR students, have you received any message on when you will be brought in TIFR?
Yes, sir. There are some different groups regarding this.
Yes, sir.
So around what time is it?
11th of January.
11th January.
11th January. So from 11th January onward, you will be brought in batches. Is that right?
Yes, sir.
After that, sir.
No. The process will start from by the end of the December, probably 28th December, and it will go up to 29th Jan. And after, if you include after the 7 days quarantine, so it will end up in the first week of February.
I see. That's very good. So finally you will be here. All right, by that time, so which means that when is the first group coming? Because is any one of you traveling in January?
Yes, sir. We DCMP students are traveling in on 11th of January.
11th
On
of January.
yeah.
Okay, so remember that our project has to get over before that.
Okay.
Because after that, you will all get busy with various logistic arrangements. So let's not postpone the thing from that. So, which batch? So, let us start actually the presentation from the 1st of January. Which batch will volunteer for 1st of January? Okay, if I don't get volunteer, I'll have to assign. So, okay, you don't have to volunteer straight away here because there are groups and you need to discuss with your group mates. But give me a date between 1 to 10 January for all of you when you will be ready to present. And don't all make it 10th of January. That's going to be difficult. So we'll stagger it at least alternate days. Okay. So now Berezinski-Kosterlitz-Thouless transition. Have you heard of this?
No, sir.
It's
Not yet.
it's like BKT transition, and it's related to some two-dimensional phase transition model like that.
Yeah, that is right. So, by the way, these two gentlemen, Kosterlitz and Thouless, they got the Nobel Prize for predicting this. So, they got the Nobel Prize only a few years back, but the work that they had done was in the 1970s. Berezinski was a Russian physicist and he did this work actually 1 year before. So he had written a paper 1 year before where essentially the Kosterlitz-Thouless transition was essentially entirely worked out. However, Berezinski wrote in Russian and more importantly, he wrote in Russian style. Now, Russian style theory papers are sort of like this 50-page papers without any figure, which are very difficult to read. So Berezinski's work did not get much publicity for both these reasons. And it was only after Kosterlitz and Thouless did their work that people told Kosterlitz and Thouless that Berezinski has done this work before, and they were actually extremely honest. They also cited Berezinski's work. The problem that happened is that they did not know Russian. So when they cited Berezinski's paper, in the first paper, they actually cited the wrong paper. They cited some irrelevant paper of Berezinski because they couldn't really read what is there in the paper. Okay, so and now it is called as BKT transition. However, when the Nobel Prize was given, Berezinski died, I think, in the 80s. So he died young. And unfortunately, when the Nobel was given, he was no longer alive. All right. So the way there is not, so now it is difficult to predict how Berezinski came with his work, but we have a very detailed account how Kosterlitz and Thouless arrived at their final phase transition model. And it starts with a very simple problem of Landau-Lifshitz. So if you read the book of Landau-Lifshitz, then you will see that there is a problem at the end. Is that you take an Ising model So this Ising model is where each of these spins can be either up or down. They cannot be anything other than up or down. And then you have a ferromagnetic interaction between the spin, which means that if they are parallel, then the interaction energy of two adjacent parallel spin is minus j, and if they are anti-parallel, the energy is plus j. So the energy difference is 2j, and it is energetically favorable for having up spins. Okay. Is it understood by everyone?
Yes, sir.
If it is understood, and I am sure that this is one of the simplest problems that you can at least state in statistical physics, what will be its transition temperature? Below which temperature will I go into a ferromagnetic state where I have a net magnetic moment? That means more than 50% of the spins are spontaneously up. Has anyone worked it out in any of the either StatMech course or
Sir,
something?
can you repeat the question?
What is the ferromagnetic transition temperature?
Uh, is it something called Neal temperature or like that?
No, it is called the Curie temperature. That is okay.
Okay.
I am not asking what it's called. I am saying what's the number. I have given you the energy scale here. What is the ferromagnetic transition temperature?
I've probably done this, but exactly can't remember at this point. By quantum using quantum, that is done.
There is no
There is
quantum
two approximate.
mechanics. There is no quantum mechanics here. This is a classical problem.
No,
So
there is two way, I guess. One in one case the Brillouin function appears, and in another case the Langevin function appears.
wait a minute. When you are talking of Brillouin function, that this is okay. Now this is exactly the mistake which Ising did. So now coming to, let me tell you some stories because we have plenty of time now. So Ising was a German Jewish physicist who during his PhD, he was actually given the Ising model by his supervisor. I don't remember who his supervisor was, someone very famous. Okay, no matter whom, he was given this and he was told to explore this model as a model for ferromagnetism. Now, Ising, of course, he did mean field theory and he got a phase transition. Okay? And it is from this mean field theory that you get your Brillouin function or whatever you are talking about. However, when you go beyond mean field theory, now mean field theory is an approximation. So I have discussed mean field theory when we did BCS theory, because BCS theory was also a mean field theory where the mean field is actually the superconducting gap, which is Ck up dagger, C minus K down dagger average into Vk, of course. So if you do the problem with mean field theory is mean field theory underestimates fluctuation. So with mean field theory, Ising could get a phase transition, but when he tried to do exactly, he could not get a phase transition anymore. And in fact, this was something which misled him very strongly. And then Hitler came, so he was sent to the concentration camp. He miraculously escaped from the concentration camp and then went to United States. But the point is, he never did any more research. So his PhD research work is the only research work of Ising, but nevertheless, he has Ising model under his name. So it was a combination of getting misled in the physics problem and also personal misfortune that followed due to the Nazi genocide. Okay, but let's come back to physics. If you don't do mean field theory, what is the ferromagnetic transition temperature? So none of you have read Landau-Lifshitz, that's obvious, because if you had read Landau-Lifshitz, you would have done this problem. What Landau and Lifshitz at the end of their book what they show is that Tc is 0. There will never be a ferromagnetic transition here. Okay? Why will there never be a ferromagnetic transition here? So this brings first to understand that we have to understand what is the elementary excitation of this, of the 1D Ising model. So the ground state is all spins which are ferromagnetic. So each pair of spin will have an energy minus J. So if I have total of n spin, then there are n minus 1 bonds, and then it will be minus n minus 1 J. That's the energy. What is the first excited state of the system? What is the energy of the first excited state?
N plus 1 minus n plus minus n minus 3j.
N minus 3j. So suppose I now take this ground state energy. If I define these as my origin of energy, so I take 0. What would be the first excited state? This is the ground state. So the first excited state is
2j, I guess.
2J. Physically, what does this mean? Physically, this means that I have half the system with upspin and half the system with downspin. And here I have a domain wall. So here I have a domain wall. And the energy cost of this domain wall is 2J. Now remember, this is the definition of a topological defect. Now Ising model does not allow you long wavelength fluctuation. It allows you only topological defect. What do I mean by topological defect? Is that if I was staying here, I cannot make out that there is a defect here. This is a very local object. If I am here, I do not know what is that there is a defect here. However, this defect is protected. What do I mean by protected? Is that though this defect is local, to heal the defect, I have to do something global. Though the defect is very local here, to heal the defect, I have to flip all these spins in one side of the defect. I cannot do something locally at the defect point and heal the defect. This is what is called topological protection. So there is, in order to heal the defect, I have effectively a large energy cost because I have to flip many spins together or one by one. All right. So this is the topological defect and this is the first excited state. Now the first excited state, there is no reason. So the energy of the first excited state with respect to the ground state energy is 2J. Now there is no reason why the topological defect has to be here. It could have been anywhere. Okay. So instead of here, it could have been here. So in that case, all these would have been down and here it would have been up. So in how many ways can I put the topological defect with the same energy? I can put it essentially in n-1 ways. All right? If n is the total number of spins.
Sir, one thing that I need to clarify. Actually, as you said that I haven't read the Landau-Lifshitz book, but is it something like you are going to show that if the entropy is something and it's unfavorable except at t equals to 0?
Yeah, that is what we will show.
Yeah. So, yeah.
That is correct. So now, since you can put this defect in n-1 ways, what is the entropy of the first excited state? It is Boltzmann constant into log n-1. Well, if you are in the thermodynamic limit and if you have a very large number of spins, is 1 you can even neglect. But nevertheless, you know that every system in thermodynamic equilibrium will go to the minimum of its free energy. That is what we have been doing in Ginzburg-Landau. And free energy is what? It is E minus Ts. Now you can see I have 2J here and here I have KT log n. Let me ignore the 1. So the moment I put one defect, I have a huge decrease in the free energy. So creating one defect is favorable. If I can create one defect, then creating two defects is even more favorable. Creating three defects will be even more favorable because that will reduce my free energy. So therefore, at any finite temperature, I will have huge number of domain walls that will proliferate and there will be no order. So therefore, one D Ising model with nearest neighbor interaction cannot order. Okay, this is what Landau-Lifshitz have done. Then there were other people and I forget their name. Let me see if I have it somewhere here. These are also reasonably well-known people. Yeah. So Dyson and Ruel what they showed is that your interaction, instead of being nearest neighbor, if they are long range, then you can have ordering. And they went one step further and they said that if your J is the interaction, if J decays as let's say 1 by r to the power n, what they showed is that If n is larger than 2, there is no ordering. And if n is less than 2, there is a very slow decay, then there is ordering. Okay? Is it clear so far? This Dyson and Ruel's proof, I am not going into it. This was a highly mathematical proof which was actually published in Communication of Mathematical Physics in 1968 and 1969. So for those of you who are interested, you could find that out.
Sir, what is J? J here? I did not understand.
Oh, I see, I see. Right, okay. J is this interaction J.
And
Okay.
this and I didn't understand why if n greater than 2 this is not ordering and less than 2 it is ordering.
No, no. So these I have not proved for you. What I am saying is that earlier we have taken what? We have taken J to be finite for nearest neighbor, and for the next nearest neighbor is 0. So I have only nearest neighbor interaction.
Yes.
Instead of nearest neighbor interaction, if I have, let's say, J that is strong for the nearest neighbor, a little less strong for the next nearest neighbor, a little less strong for the third next nearest neighbor, and so on. So it goes as Ri minus Rj to the power n. Ri and Rj are positions of two different spins. Then you see n greater than 2 means this decays very fast. The nearest neighbor is the extreme case, where it just goes to 0 after the first one. N greater than 2 is that it is decaying very fast. So if it decays very fast, then it behaves like the nearest neighbor. And then if n is less than 2, it behaves as if it has a long range interaction. And when it has a long range interaction, there is an order. So this part, that with the long range interaction there is an order, is something that I am just stating as a fact. I am not giving a proof of this here.
Sir, one clarification. Sir, can we do this using the Bragg-Williams model, because there is also a long range order present there?
Dyson and Ruel's proof I have not gone through. Probably you can. Why don't you explore this and tell us?
Okay.
Okay.
Okay, sir.
All right. So most people are happy with this. So this was a knowledge that was there for a while. But David Thouless, he was sort of a maverick who liked to work on unusual problems. And he decided that one should explore more carefully what would happen when n equal to 2. So J is proportional to Ri minus Rj whole square. All right?
Sir, I had a question. So,
Yes.
sir, the ground state here is the order state, right? So,
Ground state is in which case?
quantizing thing, let's say the first figure that you showed, when all are like, let's say, upspin or downspin. So,
That's a ground state. No, that's what I've shown you with the nearest neighbor interaction. That state you will never have. Okay, yes, you will have it at t equal to 0. Exactly 0 you will have, yes.
okay. So, what you are calling the transition then from ferromagnetic to antiferromagnetic transition, right?
No. From ferromagnetic, very few
It's ferromagnetic to paramagnetic, I guess.
From
Yeah.
ferromagnetic to paramagnetic. Ferromagnetic to antiferromagnetic transition
Sorry.
is something that no model really captures. No simple model captures it. Okay, there are complicated models that can capture these things, but ferromagnet. Right now, let's keep life simple. You have ferromagnet. When you heat a ferromagnet, what does it go into? When you heat iron above its Curie temperature, what do you get?
As paramagnetic becomes.
Exactly. And when you take an antiferromagnet and heat it, you also get a paramagnet.
Hmm.
So let's live in this simple domain. Going from ferromagnet to antiferromagnet is not impossible. In real life, there are complicated systems that do that, but that no simple model captures it. You have to put in very tailor-made second nearest neighbor approximations, take a three-dimensional lattice where, let's say, the first nearest neighbor is ferromagnetic, the second nearest neighbor is antiferromagnetic, and so on and so forth. So let's not get into those complications. They
Yes,
are
that
important
is fine,
things.
sir. My question was why there will be no transition for
Why
1D,
there
I
will
think
be
so.
no transition? Okay.
Yes.
There will be no transition because look at the free energy F here. Okay?
Okay.
This is the free energy in the presence of a domain wall.
Hmm.
So when you put a domain wall, what happens to your free energy?
Free energy should decrease.
Exactly. So therefore, creating a domain wall is energetically favorable.
Yeah.
And it is energetically favorable at any temperature. That's the catch. Because you take any non-zero T,
Hmm.
in the thermodynamic limit, N is large.
Yes.
Okay, you are talking about large chain.
Hmm.
And the moment you create a domain wall, the free energy decreases hugely. So actually, if it's an infinite chain, then the free energy decreases infinitely.
Hmm.
So therefore, you have an enormous energy advantage of creating a domain wall. So if you can create one domain wall, you can create two domain wall, you can create three domain wall, and then you keep on segregating the chain into domains of ups and downs, and therefore your magnetization becomes zero. And since that happens at any finite temperature, you have no ordering.
Okay. Okay.
Is that right?
Yeah. Yeah. Now I understand.
Yeah. So keep asking me because the mathematics is absolutely simple, but there are concepts here that you have to understand till we come to the costless Thouless transition. Okay, so now David Thouless decided he will explore if J goes as 1 by Ri minus Rj whole square. So let me switch my sharing and go to a PowerPoint slide because I have this there. All right. So now this is something that you can easily work out yourself. What will be now the energy of a single domain wall? So earlier you had seen that the energy of a single domain wall was just 2J. Okay? Now you have to calculate this integral here because you have a domain wall here, but the interaction, so this spin here, it interacts with many spins. It is slowly decaying as 1 by R square. And this spin here is also interacting with many spins. So you have to take pairwise spins and calculate their interaction and add it. So you can go in the continuum limit if you have a very large chain. That is something we have been doing all throughout. And then what you have to calculate is this integral. 1 by xi minus xj whole square, and then here you have an integral x plus a by 2 to L by 2 here, and minus L by 2 to x minus a by 2. All right, do this integral, and this is very easy to do. You will get this result. What is this result? N is actually, so A, by the way, here is the distance between the spins, and L is the total size of the system. Okay, so the total number of spins is L by A. So N is actually L by A. So now the energy of the domain wall becomes 2j log N by 4. All right. Entropy is the same. You can put the domain wall anywhere. Okay, as I said, it should be n minus 1, but n minus 1 and n in the large limit, we don't need to care about that 1. Okay, so then the entropy is kB log n. What is the free energy? The free energy is E minus Ts. Now the log n goes common. This is log n minus log 4. That log 4 is a constant. Just ignore that. N is a large number, so log 4 is immaterial. And therefore, you will get 2j minus kt log n. Now what will happen? Now someone tell me what will happen.
Phase transition will occur
Why?
at a finite temperature, because below some finite temperature the F is positive, and above some temperature is F is negative. That's why.
Yeah, so below j by twice kb, it is energy. If you try to create a domain wall, you increase the free energy hugely. Okay, because this prefactor is positive. So the moment you make one domain wall, you have a large increase in the free energy. So making domain wall is not energetically favorable. So therefore, I will be in a ferromagnetic state where there is no domain wall. Now, I cross this temperature J by twice Kb, and this prefactor becomes negative. Now, the moment I create a domain wall, the free energy decreases hugely. So now having domain walls becomes energetically favorable, and I will have a huge proliferation of domain walls, and my magnetization will drop to 0. So if this is the magnetization, I have normalized it to 1. This is how it will look. It is finite, 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 and then suddenly at j by twice kb, it abruptly drops to 0. Have all of you understood it so far? Is everything clear so far?
Yes, sir.
Okay, so Gorachand, if it is clear, then tell me what is the order of this transition?
I think, sir, first order transition. I mean, there is not continuously it goes to 0. It's a certain gap there at the particular temperature.
Okay. That is also what David Thouless thought when he first got it. But can anyone tell me why Gorachand is wrong? Can anyone tell me what is
Sir,
the
is there
mass?
any latent heat involved in the process?
Yeah, is there a latent heat or not?
Mm,
You tell me.
no,
Is
sir.
there
I
a
guess it's T
latent
delta
heat?
S, but delta S is 0. So how can there be a latent heat involved?
Yes.
Hello, sir.
Why? If no. Okay.
Can you
We can't
repeat
hear
it?
you, sir.
We
We
can't
can't hear
hear you,
you.
sir.
Hello.
Yes, Pritham, you want to say something?
No, sir, we can't hear you actually in between sometime.
Yeah,
Couldn't.
I think there was a problem with the internet. That is what I told you. Today, the internet is not very good. But I think now it is okay, isn't it?
Yeah, it's fine now.
All right. So, Amit, I also could not hear you. Can you tell me the
Yes,
argument?
sir. So, if the heat is involved, then the T multiplied by delta S should be 0. But here we see that delta is a constant. Delta S is a constant. So, uh, there shouldn't be any delta S term. The S is a constant, so there shouldn't be any delta S term.
F is a constant. Why do you
A,
say
S is a constant. It's Kb log n.
Kt log n? It's temperature dependent. It's not a constant.
Okay.
Okay, I think you are thinking in the correct direction, but you are not getting the argument right because you are not using the right definition of a order of the phase transition. Remember, a first order phase transition is where the free energy has a jump at the phase transition. A second order phase transition is where the free energy does not have a jump, but the derivative of the free energy has a jump. Okay? The derivative of the free energy with temperature has a jump. That's a second order phase transition. Look at the free energy here. Across the phase transition, the free energy does not have a jump. The first derivative does not have a jump. The second derivative does not have a jump. The free energy is just changing continuously for all orders at this phase transition. This realization, according to Thouless himself, this really got him started. He realized that this simple piece of mathematics has given him something extremely interesting because he has discovered a new kind of phase transition. This phase transition cannot be classified in terms of first order or second order phase transition. Means if you try to classify it, it will become an infinite order phase transition which has no meaning. But the point is that this is a new kind of phase transition driven by topological defects, and this is the genesis of the Kosterlitz-Thouless theory. Okay, so this work was done by David Thouless alone. So this at that time Kosterlitz was not in the picture. So David Thouless, he got this, and of course people got somewhat excited, but then you see, this is a mathematical model. Just this is a mathematical model and 1D Ising model with 1 by R square interaction. This is just too contrived. There is no known physical system which really follows this. And this argument is just for 1 by R square. We know that greater than 1 by R square, there is no phase transition, less than 1 by R square, there is a regular phase transition. 1 by r square has this strange transition. Nevertheless, as a mathematical exercise, it was spectacular because this is at least a possibility of a new kind of phase transition. So now, of course, if you there is a little bit that we have ignored here. When you are going, when you have multiple domains, multiple domain boundaries, then you have to also take into account the interaction between the domain boundaries, and that is not very difficult to do. And if you do that, you will see that instead of this being completely flat, it will acquire some small curvature here. Nevertheless, this jump will remain exactly at the temperature that it is predicted. All right. So this was the time when Howells was this gentleman who had done his PhD in high energy physics, but then during his PhD he got disillusioned with high energy physics and he wanted to move out and do something interesting. And he decided to join as a postdoc with David Thouless, who was a condensed matter physicist. And David Thouless had just done this work. So he and Kosterlitz, they discussed and decided that let us see if we can find a two-dimensional system where one can get the same physics. So where one can get a similar defect-driven phase transition. So what they started exploring, and now let me go back to my other presentation. So what they started exploring is the two-dimensional XY model. Now what is XY model? XY model is that I have a collection of spins, but now on a two-dimensional lattice, like this. Suppose this lattice constant is A and A on both these sides. So I have these spins on this lattice, and these spins, they can have component only in the plane of this screen. So they can have component only along X and Y. They cannot have any component along Z, which is out of the plane. And then they have ferromagnetic interaction. Okay, minus J psi dot Sj. And now I take only nearest neighbor. They have nothing, they have no long range, 1 by r square, nothing of that sort. They have nearest neighbor interaction. Okay, good. So I can now write this Hamiltonian in a slightly more tractable form. I take this S squared here. S is the magnitude. That's why I'm not putting a vector anymore. And then I define some universal axis. Suppose I define some universal axis and the angle of each spin with respect to that universal axis is theta. So then here I have cos theta I minus theta j. All right. Now let me assume that I am at a relatively low temperature. So this system, of course, you can solve this system and show that it will have a ferromagnetic phase transition. So at low temperature, it is ordered. So from the ordered state, suppose I do not excite the system so much. I do not go at a temperature where theta I minus theta j is very large. So, or I go in the continuum limit. Okay, let me take this. So if I have theta I minus theta j, which is not very large, delta theta is theta I minus theta j. Okay, this is what I get. Now, let me assume that the lattice constant is very small and therefore I can effectively go over to the continuum limit. So, in that case, so now this 1 and this j square, that will be a constant. Now, in the Hamiltonian, constants I can always neglect when I am looking at excitation. So, I will drop the constant. Now, if I sum over the nearest neighbor, then I have the nearest neighbor in the x direction and the nearest neighbor in the y direction. So therefore, summing over nearest neighbor, this is, so if I take any spin, it will have a nearest neighbor in the, let's say, in the x direction and in the y direction, because now it is two-dimensional and I am taking a square lattice. Okay, and if my a is very small, now I can write this as, so this js square, together I will put this as js. So js by 2 and I can write it as an integral. And this becomes grad theta square, grad theta dot grad theta. If this delta A is very small. And then here I will have dx dy, which I can write as d square r. So in the continuum limit, this is my Hamiltonian. Is everyone happy with this? Are there questions?
Sir, I can't understand the decomposition of theta in the x and y. How can you write that in this way?
Oh, the way I am decomposing it is that you see in this, here I have to sum over all nearest neighbor. All right. So if I have
Yes,
this
sir.
point here, it will have a nearest neighbor in the x direction and nearest neighbor in the y direction.
Okay, sir.
So
Yeah.
when I am summing over I here, I am summing over all lattice points, but each lattice point has nearest neighbor in the x and y direction. So I am taking these two terms here, which are corresponding to the nearest neighbor corresponding to,
Oh, okay. I will. Okay. Yeah.
right? Okay. And actually, since I have taken a squared lattice, I have a squared here and a squared here. Otherwise, we will have ax, ay, and then here. So it will become more complicated. Let's not bother about that complicacy. It will not help us in any way.
Yes, sir. It's clear.
All right. Okay. So this is the XY model Hamiltonian in the continuum limit. And okay, so I have run out of time, so we will end here. And in the next class, I will show you that this Hamiltonian will undergo exactly the same phase transition as you have seen for the 1D Ising model with 1 by R square interaction. It will undergo a phase transition that is again a infinite order phase transition, if you want, driven by topological difference. But we'll leave that for the next class. Okay. Any question that you have?
Yes, sir. One thing. All that you have gone through today is fine, but why we are studying this under the phase fluctuation course? What is the connection with these with the phase fluctuation?
How this is connected to the phase fluctuation
Yeah.
in a superconductor? You will understand when we connect it to a superconductor.
Okay.
Okay.
So
So if
these.
you want to jump guns, this theta that you are having here, later on I will map the superconductor Hamiltonian into the XY model Hamiltonian and show you that whatever happens for the XY model will happen for a two-dimensional superconductor, for a superconducting thin film. Okay. But let's not jump gun.
Okay.
If we have time, we'll do it in a relaxed way. The part that we are doing here, the mappings and so on are mathematically very, very rigorous. So this part of the phase-driven phenomena, phase transition, is the one that is theoretically the best understood. Whatever we have done before, the long wavelength ones, are much less understood in terms of, let's say, functional forms, what happens, what is the
Sir, one thing, as you have told us right now, can we have these? I just want to confirm because I have some doubt. Can we have this BKT transition in the dilute limit?
What do you mean by dilute limit?
Yeah, basically, I was guided by this thought because, okay, fine. You are saying that the BKT transition occurs for a two-dimensional superconductor, right? So, and you have told that the commutation relation between the C's become a bosonic commutation relation under the dilute in the dilute limit, right? So if the transition makes a condensation, then if the condition in the transition make a condensation, then in the dilute limit it become a bosonic condensation. But we know that in 2D we can't have a bosonic condensation. That is why I am guided by this thought.
In 2D, okay. Well, in 2D you cannot have a bosonic condensation. Why are you saying that?
Yeah, it can be shown mathematically, but that in 2D we can't have the Bose-Einstein condensation can can only possible in the 3D and 3D.
So you are talking of Wigner-Marmin theorem.
Okay, I don't. Okay.
No. So where does the thing is, what you are saying is correct, but I am trying to figure out in what context have you read it? Have you read?
Yeah. Basically, I have been taught in the StatMech class that we can't have a B condensation in the 2D, in two dimensional, in 1 or 2 dimension, right? And you have told that, and you are saying that these BKT transition occurs for the 2D superconductors, right? So
Okay,
if my
so let me ask you something which I should not ask. Who has the person who has taught you that, was he a theorist?
yeah.
Okay, so therefore you need to put the thing in perspective. Okay, the point is this. Wigner-Marmin theorem is a theorem that you should read. Wigner-Marmin theorem, you can give a search on Google also. It's a very famous theorem, and it is an accurate theorem which tells you that any system which has a continuous symmetry in 2 dimension will not order. All right?
okay, sir.
That is correct. So what the statement that you are making is correct. But then you have to also ask that this 2D system does not order, but it does not order over what length scale. That means that the correlation function, how do they decay? So what happens in 2D system, the correlation functions decay. If it was ordered, then at large distance it will go to a finite value, asymptotic value, and then the correlation functions will remain constant. But if it is not ordered over large distance, it will eventually decay to 0 at the limit of large R, large distance. In the case of 2 dimension, what Wigner-Marmin showed is that at large distance, it will go to 0. What he did not show, but later was understood, that it will go to 0 very slowly as a power law, not exponentially. Okay, so the system will not be ordered, but it will be quasi-ordered.
Okay,
Now,
so for a small length scale, or if we see locally, we can see.
But you have to listen, first listen to the full thing. It has to be very clear. So now, for example, a 2-dimensional superconductor, a thin film that is smaller than the coherence length, should not be superconducting, as per Wigner-Marmin theorem. A thin film of liquid helium should never go superfluid. These statements are correct. But then, for example, for a superconducting thin film, if you have to see any measurable resistance, you have to take a film of the size of, let's say, 7 football fields. So functionally, this Wigner-Marmin theorem really has not so much of an impact as far as no ordering is present. Because for finite size samples, you often see 0 resistance, you see 0 viscosity, you will see, if you have a spin system, you will see effective order. Is that clear?
Okay, sir. Okay, fine.
Okay. So if you want to know more about it, you should consult the book of Chaikin and Lubensky. There is a book on
Scattering.
solid-state physics by Chaikin and Lubensky, and you should read that book.
Okay.
And you will sort of see how you can estimate the correlation length. So over what length scale does it dictate?
Okay. Fine. Okay.
Okay, so this is the point that you raised is an interesting point because for a long time, the reason why Costello-Stauler's work is so important is for a long time people were exactly misled by what you said. Because Wigner-Marmin said that at large distance the order will go to 0, people thought that there is no order in 2D. So what kind of phase transition can there be? What Costello-Stauler showed was that you can have a phase transition from a quasi-ordered state. A quasi-ordered is something where the correlation function decays as a power law, to a disordered state where the correlation function decays exponentially.
Okay. I got the point. Yeah.
Okay, so all these things will get more and more clear as I show data later on. So we are not yet at the stage where I can show you data, but Costello-Stauler transition, I will be showing you data both for superfluid films and superconducting films. Any other question?
Sir,
Yeah,
we send you the write-up about the video presentation. So
I see. Yeah,
have you
I'll
seen
have a look at it. I haven't had a time to have a look at it. I'll see it. Okay, so see you. Say I'll see you either on Wednesday or on Friday. I will let you know in advance.